In this video, we're going to talk about examples for working with position, velocity, or speed, and curve length when we're talking about the parameterized vector-valued functions. So just to talk a little bit about some notation, generally speaking, if we have a parameterized vector-valued function r of t, this guy right here is going to give you position. And since change in position is equal to the velocity, when we take the derivative of r of t, that's just velocity right there. And so then what this means then is that the length of that derivative is going to give you speed, since speed is really just the magnitude portion of velocity. So one thing that we can do with this then is we can actually get like a total distance traveled over a certain amount of time by taking the integral from a to b of the length of r prime of t dt. So that's your distance traveled. Or the other way that we can think about it, if we're not talking in terms of actual speed and velocity and whatnot, we can say that that is the length of the curve traced out. Okay, and the reason for this is that speed is just like, it's like how fast that you're moving. So we have how fast you're moving times a little bit of time. So when we add up all those pieces, you wind up adding up the total amount of distance traveled. So let's look at just a kind of quick example. Let's say that a particle has position r of t equal to, let's say, t cubed, t to the fifth. We're going to find its velocity and speed. So the way that we can do that is by taking the derivative for the velocity. Apparently I'm not capable of writing that word out. Velocity is r prime of t. So in this case, that's just equal to the derivative of each of those components. So 1, 3t squared, 5t to the fourth would give you velocity at time t, and then speed is just the length of that, and that's just equal to the square root of each of the components squared and then added together. So it would look something kind of like this. So same idea as working with just like, your standard vector that we've already kind of gotten used to. We just have functions that we're plugging in for the components instead. Kind of simplifying this down a little bit, you get 1 plus 9 t to the fourth plus 25 t to the eighth, like so. And so then that would give you the speed at time t. So another thing that we can do with that, though, is find the distance traveled for a time over a certain interval. So, for example, if we wanted to find an expression for distance traveled by the particle whose position is given by that r of t equals t cubed, t to the fifth, like in that last example. So we're going to find the expression for distance traveled by a particle with position given by that for the interval 0 less than or equal to t less than or equal to 3. And I do want to point out, though, that we're not going to simplify this. We're just going to set up the expression. Okay, so the distance traveled is given by the integral from a to b of the length of the velocity vector. So that we determined to be the square root of 1 plus 9 t to the 4th plus 25 t to the 8th, and then you have dt. And then the bounds are on the integration are really just the endpoints of the integral that you're looking at. So this would be how you would set it up. We won't integrate this because we haven't really talked about the tools that we need to be able to do that. So it suffices if the problem says so to not evaluate, just leave it like that. Do be sure that you're reading the instructions carefully. Otherwise, you may wind up going to a lot of work that you don't have to. So, and it's quite common for homework problems. They'll say, okay, set up the arc length or the curve length or distance traveled expression, and then don't evaluate it. But let's look at an example where maybe you are actually able to evaluate that. So here's an example. We're going to compute the length of the curve r of t equals t cosine of t, t sine of t, 2t, when t is between 0 and 2 pi. So remember that our curve length is given by the integral from a to b, the length of the velocity vector like so. So first we're going to compute that derivative there. R prime of t is equal to derivative here. We're going to have to use the chain rule, or not chain rule, product rule, cosine of t minus t times sine of t. Same idea here. We're going to get sine of t plus t times cosine of t. And then this last one's pretty simple. It's just a 2 for that last component. So to compute the length of this guy, though, this is going to be equal to the square root of cosine of t minus t times sine of t squared plus sine of t plus t cosine of t squared, and then plus 2 squared. So if you expand all of these two out, there's a lot of nice terms that cancel out, and I'm not going to necessarily show those details here, but the results that you get when you do that, expand those out, cancel everything, you're going to get cosine squared t plus sine squared t plus t squared times sine squared t plus cosine squared t, and then plus 4 is from that 2 squared. Simplifying this down even further, using the fact that cosine squared plus sine squared t is equal to 1, you wind up getting the square root of 5 plus t squared. So that's just our speed value here, and that's what's going to go inside of this integral right there. But I think I'm going to grab a new piece of paper to be able to actually compute this guy. So our curve length, when we're looking at 0 less than or equal to t less than or equal to 2 pi. To set up the integral, we have 0 to 2 pi, square root 5 plus t squared dt. Well, that looks simple enough for now, but what we're actually going to wind up having to do to complete this integral is some trig substitution. The way that I like to do this is I like to start with my triangle like so. I know it's really common to not look at the triangle until the very end, but I like to start with this. Since this is a number plus something squared, this entire square root thing here is going to go on my hypotenuse. And we have square root of 5 for one leg and then just t for the other leg, okay? And what this means then, setting up the triangle like this, is that we can say that cosine of this theta right here is equal to root 5 divided by the square root of 5 plus t squared. Rearranging this a little bit to be able to figure out how to substitute something in for root 5 plus t squared, we get that root 5 plus t squared has to be equal to root 5 secant theta. And we also want to be able to substitute something in for dt. And if we look back here at our triangle, we see that tangent of theta is equal to t divided by root 5. So t is equal to root 5 tangent of theta. And now I can take dt. So that's root 5 derivative of tangent of theta is secant squared theta d theta. So now I can take this piece right here and this piece right here and plug them into this equation here to get a different version of my integral that would be easier to work with. Notice that I am not using my limits of integration anymore. When I work with substitutions, my preference is to just drop them while I'm working with the substitution and then worry about them when I plug everything back in at the end. So that way there's less opportunity for mistakes. So this guy right here winds up becoming root 5 secant theta, and then we have a root 5 secant squared theta, and then that d theta there goes in for dt. So we have 5 times the integral of secant cubed theta d theta. Great. Okay, so what do we do with that? Well, there's like a power reduction formula that you can apply, and what you wind up with when we do that is 5 times secant theta tangent of theta divided by 2, and then adding to that, you still have the 1/2 integral of secant theta d theta. So just a little note here, this is a reduction formula that we just applied. So now at this point, this gets kind of left alone because we're more or less done with that for now. And then we're actually able to take this integral fairly easily. It's 1/2 natural log absolute value of secant theta plus tangent theta. So that's all of that right there. But everything is in terms of theta. We don't want theta. We want everything in terms of t. So I'm going to go back through and plug everything back in. I have an expression for tangent of theta, but I don't have one for secant theta. So to get that, I'm just going to kind of rearrange this line right here. This is equal to root 5 plus t squared divided by root 5. So plugging everything back in to get my t's back where they belong, we're going to get root 5 plus t squared divided by root 5 times t divided by root 5, and then this was all still over 2, so that's times 1/2, and then plus 1/2 natural log of root 5 plus t squared divided by root 5, and then plus t divided by root 5. Okay, so we've now taken our integral, but we still have to evaluate its endpoints. So that integral from 0 to 2 pi of that root 5 plus t squared that we were going for is equal to 5 times root 5 plus t squared divided by root 5. times t over root 5 times 1/2 plus 1/2 natural log of, and I'm just going to lump these together, root 5 plus t squared plus t divided by root 5. And then all of this is evaluated from 0 to 2 pi. So for this piece right here, when you evaluate it, I'm going to leave those details to you, but this is more or less the process of what it would look like to try to compute the integral for a curve length. So it kind of maybe started out looking deceptively simple and tidy, but in order to be able to do this whole process, we had to go through a trig substitution, plug everything back in, and then we're able to evaluate from 0 to, this is a 2 pi up here. So that's pretty much it on curve length and velocity and speed and all of that stuff. So yeah, we will see you next time.